Welcome to ETAP webinar, ETAP Intelligent Microgrid Management. My name is Mohammad Zadeh and I'm your presenter today. This webinar includes two parts. Today I will present part 1, microgrid design and software-based validation. Part 2 that focuses on system architecture, control logic validation, and advanced monitoring will be presented on May 13, 9 a.m. Pacific time and May 14, 9:30 London time. In this webinar, first we review microgrid control system and mainly discuss the role of microgrid controller. Later, we review pains and challenges of implementing a microgrid controller. Also, we look into the need of microgrid controller model during simulation and design stage. ETAP offers a model-driven microgrid controller that addresses the aforementioned challenges. It also includes a digital twin that can be utilized from design to operation stage. It also has several built-in functions that meets the requirements of most microgrid applications. In this webinar, I will demonstrate a microgrid system simulation and analysis using ETAP, where ETAP Microgrid Controller Digital Twin is used for performance evaluation. Let's start with the microgrid control system definition. What is microgrid? Microgrid is defined as a cluster of interconnected distributed energy resources, including energy storage systems and loads that can operate in grid-connected and islanded modes. Compared to a single distributed generations or DERs, the microgrid can provide more technical benefits, control flexibilities, economical operation, as well as better means of improving energy efficiency. Dispatchable resources, especially energy storage systems, are key assets to enable microgrid operation in islanded mode. In addition, energy storage system can maximize and facilitate seamless integration of renewable energy resources by allowing to control the microgrid import-export power at the point of interconnection. This allows microgrid to be more like conventional loads from the electric grid perspective. To manage and control microgrid dispatchable assets, a microgrid control system is required to determine dispatchable quantities based on various possible objectives and constraints. Furthermore, microgrid energy resources can be employed by the microgrid control system to make microgrid operation possible in the islanded mode. A microgrid control system can be physically implemented in a centralized or distributed manners. In a typical configuration, microgrid control system is realized by a microgrid controller that is located close to the microgrid point of interconnection. This controller communicates with local controllers that directly or indirectly control microgrid dispatchable assets, as well as point of interconnection circuit breaker and other switches or breaker controls and relays within the microgrid. IEEE Standard 2030.7 2017 provides technical specification and requirements for microgrid controllers. As per this standard, 3 levels of control functions are defined for microgrid control system. Level 1 control functions are lower level functions that are supposed to be implemented at distributed energy resource, load, or device level. Level 2 control functions are the ones required at the microgrid point of interconnection level to facilitate transition between grid-connected and islanded modes of operation, as well as simple rules to dispatch microgrid. Level 3 control functions are higher level functions that perform supervisory control. A microgrid controller can typically provide level 2 control function as well as some of level 3 supervisory control functions. Power exchange control of a microgrid system at a point of interconnection or point of measurements, POI or POM, is one of the main functions of a microgrid controller. Power exports from a microgrid that is not consumed by the nearby loads in the system can exceed the reverse power pickup points of the network protectors and in turn can create an unintended islanded conditions for the microgrid system. As an example, from ETAP Microgrid Controller performance evaluation, it can be seen that Microgrid Controller dispatches the energy storage systems to charge when the generation exceeds the power demand within 1 to 7 o'clock in the morning. So this is the orange area here. So as you see, the energy storage basically is charging because there is an excess of renewables as compared to the load. Then the microgrid controller dispatches the energy storage to discharge during the peak power demands during the times 1 to 2 afternoon, here, the blue basically area, and around 6 to 10 p.m. here, again, is trying to do the peak shaving. So the microgrid controller dispatch algorithm has also curtailed part of the wind energy generations for a few hours here at the beginning to meet various microgrid controller demands. Again, that's a very specific microgrid with higher penetration of the renewable in the system. So this is one example of what the microgrid controller does. Load shedding is typically required in microgrid application in case of islanding or loss of generation in islanded mode of operation. Generation shedding may be also required at both grid-connected and islanded modes of operation if microgrid contains larger generation sources as compared to its load and it doesn't have enough energy storage capacity. As an example, from ETAP Microgrid Controller for the studied cases, from about midnight to 8:40 a.m., so midnight to 8:40 a.m., there is enough generation and energy charge in the storage that in case of an islanding, there is no need of load shedding. While within 8:40 a.m. to 1:40 afternoon and around 3:40 to 11:20, there is a need of certain amount of load shedding, and that certain amount can vary in time as you see, to be able to maintain the load and generation balance. So load shedding and continuous updating of the strategy of the load shedding is one of the key functionalities of a microgrid controller. Another application of a microgrid controller is renewable smoothing. So renewable resources are intermittent due to the fluctuating weather condition, in particular wind speed and solar irradiation. Intermittency in active power flow may cause various problems for the power grid, for the voltage profile and quality of the power fed to the system. Several grid codes also mandate microgrids' rate of exchange power with the grid to be limited to the certain value. Energy storage resources can be dispatched by a microgrid controller to compensate renewable resource fluctuation. As an example here from ETAP Microgrid Controller, rate of active power change has been limited to 150 kilowatt per minute by charging and discharging the battery storage. So as you see here, the blue curve is the original curve that is basically the power produced by the renewable. As you see, you have a fast fluctuations, sharp fluctuations, while the gray is the battery and renewable together that is trying to smoothen the curve by reducing those sharp changes in the profile. Again, this is another example of a microgrid controller functionality. So by now we have a good understanding what microgrid controller is, what it does, and we also learned some of the examples, some of the functionalities that a microgrid controller can have. Now let's look at the pains and challenges of implementing a microgrid controller. Microgrid controller strategy and associated control functions heavily depend on the type of the microgrids and its assets, ratings and sizes, operation conventions, and reliability requirements. A microgrid controller designed for a grid-connected microgrid with mainly inverter-based resources may not be possible to be adapted for a microgrid with a major combined heat and power plant or a permanently islanded microgrid with mainly rotatory machines. To implement a microgrid controller, one approach is to program a generic controller fully or partially to meet microgrid requirements. This approach offers considerable flexibility to achieve desired control functionalities, though it may have several limitations as the programmability of a generic controller may be limited to a certain level. In addition, this approach requires an extensive expert engineering effort to develop, enhance, and then test or enhance formally developed control function for each microgrid project. This approach also limits microgrid control functionality to simple ones like level 2 functions and may not be suitable to implement complex and more sophisticated functions such as level 3. For instance, if you want to do some sort of an optimal dispatch and more sophisticated algorithms. Another approach is to develop a generic microgrid controller with predefined functionalities. Typically, microgrid sources, loads, and energy storages are defined within this type of microgrid controller through user settings. In this approach, type of resources, constraints, and overall objective of the control are part of that predefined functionalities. The main drawback of this approach is that any new requirements or functionalities that is not supported by the existing control functions may not be achievable without an additional product development. For instance, if microgrid controller does not support controllable loads or curtailable renewables, supporting such assets requires enhancing control logic or firmware and software. Furthermore, a generic microgrid controller becomes sophisticated and less optimal to potentially accommodate many functional requirements, while some of them may not be needed for certain microgrids. Both generic or programmable microgrid controller has too many settings to define microgrid, capture various resource ratings, operational constraints, and control objectives. This makes it very difficult to work with this type of microgrid controllers. In the feasibility study stage of any microgrid project, it is also required to determine the optimal sizing of renewable energy resources as well as energy storage system. Dispatch function within microgrid controllers plays a significant role to determine the behavior of the microgrid system. In case of a generic microgrid controller, typically the model of the microgrid controller is not available within the power system simulations and analysis software. Hence, it's not possible to correctly perform feasibility study unless it's done by the microgrid controller vendor. In case of programming a controller to realize a microgrid controller, details of the expected microgrid control function should be known in advance at the stage of feasibility study. That is very improbable. In addition, the selected power system analysis tools needs to have a capability to model, simulate microgrid controller logic within the time domain analyses. In addition, in order to test and validate a microgrid control performance, we always need tools and test setups that are typically very sophisticated, and typically a hardware-in-the-loop type of test setup is required to validate the performance, which is costly, it's time-consuming as well. In case of distribution system microgrids, microgrid system including resources, loads, and network can be dynamically changed due to the system restorations and operational needs. This makes it even very difficult or almost impossible to use conventional microgrid controllers. ETAP solution to address various challenges of realizing a microgrid controller is a model-driven platform, which is a patent-pending technology that executes virtualized functions. Overall functionality can be configured by easily mixing pre-developed and validated control functions to realize a required microgrid controller. User can also definitely develop its own logic on top of the built-in functions. One of the key features and one of the key elements of this solution is that this microgrid controller has a digital twin by nature, and we'll talk about that in more details. So when we say ETAP Microgrid Controller is a model-driven solution, what do we mean by that? Model-driven solution is the solution that is fully aware of properties and connectivity of their systems and their assets, and it can utilize that information to perform various tasks. In case of a microgrid controller with built-in functions, microgrid must be defined through plenty of settings for the microgrid controller. Model-driven approach minimizes the amount of settings required to describe system data for the control function. For instance, in the context of the microgrid controller, energy storage settings and properties such as charging and discharging ratings and efficiencies and storage capacities are all known to the model-driven microgrid controller, and additional settings are not required within microgrid controller to define energy storage ratings and properties. This significantly not only reduces the amount of complexities of the settings required, but it also gives an elegant user interface to set microgrid controller. Model-driven approach allows utilization of predictive simulation to enhance or achieve certain required control functionalities. For instance, in the context of microgrid controller as shown, power system analysis software, which in this case would be on the top, okay, that has a capability to perform dynamic stability for different load shedding strategies that are devised by a microgrid controller, can be evaluated in the simulation environment during the real-time operation to validate which case actually can maintain the stability of the system during the transitions from the grid connected to the islanded mode of operation. ETAP Microgrid Controller is designed to handle virtualized function. This means that built-in functions are hardware independent that are defined by input-output settings. Definitely, processing power and memory requirements shall be considered. These functions are cross-platforms, and this means that it can be executed both in an online and offline environment and in Windows and in Linux. And this allows us to run a virtualized function both in simulation and as well as in the hardware when the controller is actually working in the field. To also realize such functionalities, time is also a virtualized quantity that is defined and consumed by a virtualized function. As mentioned earlier, depending on the needs of a microgrid controller, different functions can be combined to meet microgrid functional requirements. This technology, as it is obvious, is the enabler of digital twin. Microgrid control functionality implementations and settings have significant impact on effective and optimal utilizations of energy resources within microgrid. In order to determine proper size of renewable energy resources, energy storage ratings, and capacity of them at the stage of feasibility study, it is significantly beneficial to have access to the model or digital twin of the selected or expected microgrid controller. One of the key features of ETAP Microgrid Controller is the availability of its digital twin that can be used as a true model of microgrid controller within the simulation study. The digital twin can be used for evaluations, for testing, as well as fine-tuning optimal controller settings. In fact, in ETAP Microgrid Controller technology, we develop and test the digital twin first in an ETAP simulation environment, and then once you're happy with its performance, we deploy the digital twin to a controller hardware and test it within a HIL test setup. So more information about how the hardware works, what are the specifications of the hardware will be provided in the part 2 of the microgrid controller webinar. When we are talking about the digital twin, means that we need to have an element representing that controller in an ETAP software. So we have added a new element called controller. As you see here, I have the microgrid controller implemented or represented by the controller element. This controller element, as I'll go through the ETAP and demonstrate, can monitor and control other elements within the system. It runs in the time domain analyses, like transient stability, and in transient stability we only support for now the AC elements, while in time domain unbalanced load flow analysis the controller can monitor and control both AC and DC elements. As I mentioned, ETAP Microgrid Controller comes with the built-in functionalities, but user has a capability to either enhance or add some control logics on top of the built-in functions. That can be done through a graphical user interface as shown here. One or multiple user-defined modules which are graphical can be used, or user can do scripting and generate a DLL with the basically interface that we provide and the XML to define the logic settings, and a user can use that DLL if they want to create their own logic from scratch or on top of our built-in functions. So let's start the demonstration. So I'll go to ETAP and first I demonstrate the controller elements, and then I'll start demonstrating a few functionalities of our microgrid controller that are most important for microgrid application. Okay, let's start by looking at the controller element. Basically, controller element is a new element in ETAP where user can define as some associated devices. Let's say in the case of a microgrid controller, your microgrid controller can be associated to the microgrid assets or resources. So in this case, microgrid controller may monitor the transformers, the renewables like wind or PV, your loads, your energy storage, if you have STATCOM or capacitors. So it can monitor as well as it may control some of your assets here. So you may have also communicating between one controller to another controller. Let's say in this case, I have a microgrid controller talking to my battery controller. So my battery controller basically is a controller that basically controls the inverter that is connected to a DC battery to emulate a commercial battery with inverter that's used in a microgrid application. As you see here, let's say for a battery, you're only talking to probably some circuit breakers, to an inverter, to the transformer, maybe in the system. Now, in a microgrid controller, first the association gets defined, means that what are the devices that are observable and controllable. The next thing is that you can define some user-defined logic in case we have. You may have a DLL controller where all the settings and logic is defined in the controller. In case of an ETAP microgrid controller, basically a microgrid controller is a bunch of DLLs that are worked together, and you can see its digital twin in ETAP and load it in ETAP and see basically the settings. So in this case, as you see here, I have a bunch of functionalities here that in case I want to define, let's say, some operating limits. I may have some operating limits for my energy storages. I may have some settings for my active power control, whether I'm using rule-based or other type of dispatch logic. I may have economic dispatch with the settings to define how my economic dispatch works. I may have a rule-based dispatch with a bunch of settings. The settings to define how the transitions from the islanded mode to the grid connected to the islanded mode works. I may have some settings related to the renewable smoothing, which logic I'm using, and basically the settings related to the logic for renewable smoothing. I may have a reactive power control that basically performs different modes of reactive power controls, and a bunch of other things that can be defined that are definitely settings of the control logic within the microgrid controller. Again, in a model-driven approach, let's say it's settings related to the PVs or VINs, their ratings, their sizes, they're all coming out of the ETAP model. So in the microgrid controller, you don't need to have too many settings to define the microgrid, its connectivity, it's basically settings of different assets and ratings. They're all known because this is a model-driven solution. Now, let's start with a simple example. In this microgrid, I have a wind, I have a solar, I have some loads, I have a battery, I have some reactive power resources. I've put both capacitor, switch capacitor, and a STATCOM here for the sake of just demonstration. Now, what I'm going to show to you first is that in this microgrid, one of the key constraints is that the microgrid is not supposed to export power to the grid. So what we want to do, we want to utilize our battery to charge the excess of the energy in the microgrid when there is excess, and discharge when, let's say, the import power goes above a certain value. Let me take a look at here in the rule base, let's say, is above 2 megawatts. So if the input power goes above 2 megawatt, we're going to start utilizing a battery. So for this case, I've already ran the case. Again, we are running through the time domain load flow analysis. So we can actually run with the time step, let's say 1 minute here. And I have my wind and solar profiles that I'm looking for this microgrid defined. And I'm going to run for a period of, I think, 2 days. So I'm going to run for 2 days and see how my microgrid controller behaves. So I have actually done, and I'm plotting the performance of the microgrid. So the bottom figure here is the case that there is no microgrid controller. So what happens is that between time midnight till, let's say, around 6 o'clock in the morning, 6:30, what happens is that we are actually exporting power to the grid. The negative value means exporting and positive value means importing. So as you see in this microgrid during the night time, there is not that much load. There is a renewable wind power, and we're exporting. So in order to take care of this exporting, what happens is that we are using our battery to charge and discharge. So let me go just to the case of a rule base and go to my inverters for both of my batteries. Let's plot the power. So I have 2 batteries in this system. So what happens is that in case of a rule-based dispatch, what happens is that between basically midnight till 6 o'clock, I'm charging my batteries. And the moment that the import power goes above 2 megawatt, I'm actually starting discharging my batteries. And as you see, as the power goes up and I have enough state of charge in the battery, I'm gonna basically curtail and shave the peaks and discharge. Again, this is at 48 hours of simulations, and I'm charging midnight till 6 o'clock and discharging later in the day when there is a import power above 2 megawatt. Again, this case doesn't care, is a rule based. The first time that it sees the power going above 2 megawatt, it's going to discharge. So in reality, you see that it didn't do a good job in peak shaving. I still have around 8 megawatt import power from the grid. Now let's try to use more sophisticated algorithm for active power dispatch. So in this case, we are using the economic dispatch logic. So in the economic dispatch logic, what the microgrid controller does, microgrid controller is going to use the load and generation forecast. It's going to look at the energy storage capacity and the constraints of the system, where in this case is to make sure that we do not export to the grid. And also we have a cost associated with the importing power from the grid. So what it tries to do, it tries to minimize the cost of importing power from the grid while it's maintaining the constraints, which is not exporting power to the grid. I've already ran the case for the economic dispatch, and as you see here, I have power imported from the grid, from the point of interconnection, in the case as there is no microgrid controller for 48 hours. As you see that we are exporting for a few hours, then we are importing, and then again we're exporting, and then we're importing. Now if we have a ETAP Microgrid Controller with its built-in economic dispatch logic, what it does, first for the first 24 hours, it just monitors the system and be able to basically utilize that information to do a load and generation forecast for the next 24 hours. So the microgrid controller in the next 24 hours kicks in and basically commands the energy storage to charge and discharge to first zero the export power to the grid, and also minimize the cost of importing power from the grid. As compared to the rule-based, in this scenario, as you see, is that it does a better job of peak shaving. The import power that was about 8 megawatt now has been reduced to around between 5 to 6 megawatt by utilizing the energy storage. Again, the economic dispatch uses more sophisticated algorithm, looking at the forecast of the load and generations, the energy storage capacity, and utilize the energy stored in the battery to minimize the cost of importing power from the grid. Now let's look at another application of ETAP Microgrid Controller, which is renewable smoothing. So what happens in microgrids, as I mentioned, with the renewable resources, due to the weather condition, the output power of the renewable can be fluctuating. So what happens is that this fluctuating power can create problems for the grid. It can create a problem for the voltage profile in the system. So whenever we have an energy storage in the system, we can take benefit of a portion of the energy storage capacity to compensate the fluctuations of the renewable, so we can smoothen the overall power of the renewables and battery together. So in this case, if I actually show you the power of the point of interconnection, as you see here, for the case that there is no renewable smoothing, and I'm looking at my point of interconnection power, and let me do that. And as you see here, what happens is that there is a rapid fluctuations due to this basically fast wind speed change, or it can be a cloudy day. Our solar can change the same way too. So in this case, as you see that I have a very sharp power increase or decrease of my basically renewable at a point of interconnection, that can create problems for the grids, for the microgrid voltage profile and the grid voltage profile. So in order to address that, so what have we done in ETAP Microgrid Controller? Basically, let's go to the AC cable, tie cable, and let's plot the power in this case. So if I put them side by side, you see that what we have done, we have limited the rate of change. So you see that in cases there's a sharp drop, we actually limited the rate. Our microgrid creates a nice Excel report that we can see here. Actually, the blue curve is the point of interconnection power without renewable smoothing, and then we are utilizing a battery by charging and discharging to actually smoothen the power. So the gray curve is the overall power of the battery and renewable together. And in this case, as per our settings, if we go to DLL, if we go to the renewable smoothing, we wanted to, for the case of renewable smoothing, we wanted to basically limit the rate to around 150 kilowatt or 0.15 megawatt per minute. So if you want a more smoother curve, you can actually reduce that rate, and that means that actually you need to charge and discharge your energy storage more, and you need to have a bigger capacity. So if you're using energy storage for the sake of renewable smoothing, it's really important to perform this analysis to figure out what is your storage capacity to be able to successfully do the renewable smoothing. Another important microgrid controller application is reactive power control. So typically microgrid controller is expected to coordinate different assets of the microgrid to maintain a certain voltage set points or power factor set points at the point of interconnection. So in this scenario, actually ETAP has a comprehensive reactive power control where you can define multiple modes of operation and set points that you can switch. and you can define which assets can be used for the basically reactive power control. You can use your STATCOM capacitor, you can use your renewable resources, your battery, and you can define the priorities of using them. Let me just go to the reactive power revision so you can see that better actually. So here again, many things can be set in the reactive power control. You can set basically which control mode we are using and what are the different set points, and if there's a PI controller that takes care of the control of the voltage or power factor reactive power. We can define which energy storage you want to use. If you have a capability curve, ETAP again is a model driven. It goes and take care of the capability curve from your renewables, your inverters, and consume that to make sure that when it commands the asset, it follows the capability curve of different assets. So what I'm trying to demonstrate here is that this is the case that first microgrid controller does not do any reactive power control. So first is disabled, and we're going to look at the voltage at the point of measurement, which is basically here in the system, this bus, the main microgrid bus that is connected to the point of interconnection. So as you see here, voltage is actually below 98%, and as the power fluctuates, we have wind fluctuating or our solar fluctuating, you see that the voltage actually fluctuates and is actually below that 100% that's typically is expected. Now when we have a reactive power control, so what the microgrid controller does, it basically goes through the assets in the system, and based on the algorithm that it has, first it tries to use a switch capacitor or capacitor, then it tries to use the STATCOM, and then it tries to utilize the energy storage renewables in the system. So as you see here, we also has changed the set point somewhere in the middle, like around 10:30. We actually increased the set point from 100% so to the 103. And as you see here is that when it is reactive power control, what has happened is that the microgrid controller commanded and dispatched their assets to maintain 100%, and when it was set to 103%, it tries to maintain that. You see that sometimes it drops because what happens is that if we go and plot actually our capacitor in this scenario, let's plot the capacitor reactive power, and then let's plot the go to the inverters, plot the batteries and the STATCOM reactive power, and then what happens if I go to make these plot like that. So let's get rid of this. So what happens here is that when it comes to the capacitor, we are fully utilizing a capacitor when we go to 103% voltage, and we are also consuming our battery and STATCOM full capacity. So what happens is that the next we're going to use actually our renewables. So in this case, let's say we are using the ACPV array. Let me plot the reactive power of the ACPV array too. So if we have capacity in our ACPV array, we're going to use that, but as the PV first priority is to inject active power, and if the PV gonna inject more active power, it has to reduce the reactive power based on the capability curve. So what's going to happen is that voltage may drop. Again, it depends on the design of the system better. Do we want to 100% guarantee that the voltage is maintained? Means that we have to actually resize or increase the size of our capacitor STATCOM to meet that. But in this scenario, it shows that how the microgrid controller can utilize different assets to maintain the voltage. As you see here is that 100% is maintained, 96% is almost maintained, but when it comes to the 103, for this specific microgrid, maintaining 103 is not guaranteed. So it means that if a client wants to maintain that, it needs to add more reactive power sources to the system. Again, that's very important, that how the microgrid controller coordinates the reactive power among the different assets to maintain the voltage at the point of interconnection or point of measurement. One of the key feature of any microgrid controller is to devise a load shedding strategy for the microgrid system. So whenever the microgrid wants to transition to the islanded mode, the local controllers, relays, or assets or resources in the microgrid know what exactly to do when the islanding happens. So basically, a microgrid controller keeps looking at the resources, how much generation we have, how much energy storage has energy in it, how much load we have, how much we're importing, and saying that if at this moment we basically get disconnected from the grid, what should happen, which assets, which loads or generations needs to be shed to basically provide a balance, and convey or communicate that strategy to the resources to make sure that if the case happens, that the local controllers relays know how to respond to that. So in this scenario, in order to simulate that, first of all, our microgrid controller has basically several settings on how basically we do the load shedding. Again, I don't want to go to the too much details, but basically we say that basically if our microgrid has a grid forming inverter, if you're intending to use that as a means to stabilize the frequency, which loads can be shared, what are the curtailable generations if you have an excess of the power. Again, model-driven approach, it knows everything about the microgrid. The other thing happens is that we have relays or local primary controllers that basically we simulate that, and what it does is basically based on the amount of load that needs to be shared, it knows that with which priorities, which loads and circuit breaker needs to be basically user can set and work with that. So in a very high level, at every executions of the microgrid controller that can be seconds or minutes, it looks at the system and says that what if I lose this circuit breaker, what if I lose the grid, this amount of load or generation needs to be shed. It gets conveyed that to the local controllers, and those they know basically they can figure out how much load, basically which loads to shed based on the request of the microgrid controller. So each local controller has a transfer trip from the circuit breaker. So the moment that circuit breaker trips, the battery immediately switches to the grid informing, the loads, basically the relay knows how much load to trip. So the microgrid controller has done the job beforehand, and it keeps updating the basically what needs to happen when the load shedding occurs. So in this scenario, at time 2 seconds, there is a fault on the line. So this is a running transient stability analysis. So it's not anymore time domain load flow. So at 2 seconds, there is a fault. The relay actually trips the circuit breakers and we get disconnected from the grid. So at this moment, what happens is that basically the battery gets converted to grid forming, tries to inject, voltage is very low. So immediately battery starts to basically bring up the voltage to the 100%. And we, as you see here, we are immediately after the circuit breaker trip, we are shedding the loads. So we know that actually microgrid controller has already communicated what needs to be shed ahead of time. So in this scenario, again, user can go to the transient stability analysis results and look at how the system actually performed. It can basically go to the POM voltage and see that how the voltage gets recovered in this scenario, or you can look at the battery in this scenario. If I go to the basically my battery transformer, if I go to the branch to the battery 1 or battery 2 and look at the megawatt 2 and plot those, and you see that the battery actually responds, and as you see here at the time 2 battery response and start producing more power to basically take care of the problem in the system, which basically we got the grid forming and we got disconnected from the system. As I mentioned earlier in this webinar, user might need to sometimes customize the logic, or they want sometimes even to write the rule-based logic from scratch. So one of the mechanisms that a user can use is the user can define a bunch of graphical logic and define execution rate, and we can actually run those logics within the simulation environment or in the hardware, in the controller, and do the job. So in this scenario, actually, as you see here, that what we have done, we have created a kind of a rule based dispatch. As you see here, is that user can use a graphical diagram to actually take care of how to command a battery in the microgrid to basically do the same thing as we explained before, that we want to minimize the export to the grid, and it has certain rules how to actually discharge when we are importing power from the grid. Again, you can use a graphical approach. You have access to the voltages, currents, powers. You can write and you can command to the PQ or the currents of the battery, and this actually can do the job too. So this is another approach that can be used just to show you the response of this case, that graphical logic makes sure that there is no export power to the grid, so you don't see a negative number. So it's always about importing, and as the power goes up, we are actually chopping the current to maintain, basically to do some sort of a peak shaving in this scenario. Again, user has the options whether to use built-in functions. You can use write logics on top of that using a graphical interface, and you can also do scripting as well. They provide a very elegant interface when it comes to the scripting and writing the logic using scripting tools. In this webinar, first we reviewed microgrid control system and mainly discussed the role of microgrid controller. Later, we reviewed pains and challenges of implementing a microgrid controller. Also, we looked at the basically a need of a microgrid controller during the design and feasibility study stage. ETAP offers a microgrid controller, is a model-driven solution that addresses the several challenges that's in the implementing a microgrid controller. Again, it's a model-driven based technology. It utilizes virtual functions, and also it has a digital twin. ETAP offers several built-in functions to meet the needs of most microgrid control application. Again, it offers rule-based dispatch, economic dispatch, renewable smoothing, reactive power control, rate control, intelligent load sheddings, and there are other type of functionalities that, for the sake of time limitation, we couldn't cover that in this demonstration. So the key important thing here is that we have a technology that this technology allows us to be able to easily and quickly create new function, enhance existing functions, and basically we are developing a digital twin, and the digital twin can be deployed into the hardware and be executed. With that, I'll invite you to the next webinar, part 2, that's been a week. And that one will show and demonstrate basically the hardware aspect of it, how you can actually test it in a real-time environment, and how ETAP real-time monitoring can be utilized with the ETAP Microgrid Controller to have a solution that meets all the requirements that's needed for a microgrid control solution. So with that, I would like to thank you for listening to this webinar. Don't miss the part 2, and I'm more than welcome to any question. Thank you.